Yeah. So in previous video we started discussion of the some organic reactions from the one of the very famous book, that is Organic Chemistry, which is written by Jonathan Clayden, Nick Greaves, and Stuart Warren. So in our previous video we started the reduction reaction. That means here chapter 23, that is a chemoselectivity and protecting groups. So you know this chapter, chemoselectivity and protecting groups. So now let us continue this chapter from the that reduction of the carboxylic acids to alcohols. Okay, so here in this case, carboxylic acids can be reduced by lithium aluminum hydride to alcohols. Okay, so actually here that sodium borohydride cannot reduce this carboxylic acid. Sodium borohydride is a weak reducing agent than the lithium aluminum hydride. So here in this case, while lithium aluminum hydride is a more reducing agent than the strong reducing agent than the sodium borohydride, that aluminum hydrogen and boron hydrogen. This one is a more electronegative difference here, boron and aluminum. That boron is a more electronegative than the aluminum. So for aluminum electronegativity less, and the hydrogen electronegativity 2.5 here, 2.5. So this bond has a more electronegative difference. So with increasing more electronegative difference here, this one carries a more positive charge, this one carries a more negative charge. That means here this hydrogen has a strong nucleophilicity. Here in this case, less electronegativity difference here, less magnitude of the negative charge here, less magnitude of the positive charge. So it is a less nucleophilic. So that's why sodium borohydride is a weak reducing agent than the lithium aluminum hydride. So lithium aluminum hydride almost reduce all functional groups, but not sodium borohydride. So sodium borohydride reduce only aldehydes, ketones, acid halides. That's it. But lithium borohydride, that LiBH4, it is slightly strong reducing agent than the sodium borohydride. So it can reduce aldehydes, ketones, acid halides, and additionally esters also. So now coming to this lithium aluminum hydride, that is more reactive, so that reduces almost all functional groups. So now coming to the carboxylic acids, that carboxylic acids are reduced to alcohols by lithium aluminum hydrides. Okay. So here the one more key point in this reduction reaction. So actually here first carboxylic acids on reaction with this ALH4 minus, first acid base reaction takes place, RC here O minus here H2. Okay, first of all acid base reaction takes place, of course by the multiple steps, that is also reduced to the alcohol. So here in this case balanced equation is the carboxylic acid on reduction with lithium aluminum hydride will get the alcohol RCH2OH. Here in this case here 3 moles of the lithium aluminum hydride can reduce the 4 moles of the carboxylic acids. Okay, so actually in this case for each carboxylic acid reduction into alcohols, 3 hydrogens are required. Okay, first acid base reaction, and next it is converted to aldehyde, and aldehyde to alcohol. Totally 3 hydrogens are consumed. So here 4 into 3, here 12 hydrogens, here 3 into 4, 12 hydrogens totally. So here the important point is that 4 moles of carboxylic acid can be reduced by the 3 moles of the lithium aluminum hydride. And the notable point is BH3. The BH3 is the very selective reagent for the carboxylic acids. BH3 borane is a very selective reagent for the reduction of the carboxylic acids. So actually here borane has some specialty that reduce the electron rich compounds actually. So with a diborane, actually first of all here also acid base reaction takes place. So here in this case H, here BH2. Here in this case 2.5, here that boron is less electronegative than the hydrogen. So here this one carries a negative charge, this one carries a positive charge. So H minus remove the H plus. So by the acid base reaction we will get this compound boroacetate and 3 moles of the H2. And now here by this one on furtherly reduced to the alcohol. That's it. So here finally carboxylic acid is reduced to the alcohol with the borane. Okay. Now here, so let us discuss here some examples. So here we have taken that BH3. Here BH3 is we have a specific specificity, that means here that can reduce the aldehydes and ketones and carboxylic acids and amides. Okay, that can reduce the carboxylic acids, amides, and readily, but not esters, acidic halides. Okay, esters and acidic halides are less reactive towards BH3 reagent. So in this case, that BH3, there is the ester and carboxylic acid group. So BH3 generally that can is a more selective for the reduction of the carboxylic acid group. So here that ester remains unaffected, carboxylic acid is reduced, is the most important reaction this is. So CH2OH, that's it. Now here in this case again here reduction with the BH3, here ketone is there and carboxylic acid group is there. Between these two here, the carboxylic acid is a more reactive towards BH3 than the ketone. Okay, so though here in this case ketone remains unaffected, carboxylic acid is a more reactive. And now this one here contains COH and ester. BH3 is a selective reagent for the reduction of the carboxylic acid. So here it is reduced CH2 and OH, and this is the ester one remains same. BH3 slowly reduce the ester. So almost here no reaction with the ester. That's why carboxylic acid is reduced. Now here lithium borohydride reduce the esters but not carboxylic acids. So it is a very chemoselective reaction. C double bond O here OH, and it is reduced. So CH2OH. Okay. So that's it. So in this case here, first of all, first suppose this one on acidic hydrolysis, acid medium hydrolysis, actually ester is hydrolyzed to carboxylic acid, so is the carboxylic acid. So this one further heating, just here loss of water molecule, so intramolecular esterification takes place. So here product is double bond O, this is the oxygen, and above the plane methane, so that lactone is formed. Now here in this case, this one on further heating is alcohol and carboxylic acid, so loss of water molecule, so product is oxygen and double bond O, and this is the methyl. Okay, so here in this case, what is the relation between these two? The relation between these two is the enantiomers. Okay, these two compounds are enantiomers. How these are enantiomers? It is a chiral carbon, it is a chiral carbon. Okay, so let us try to give the configuration for this one. Here CH2 CH2, here CO and CH2. So CH2CO, CH2CH2. So this one has a high priority and this one has a second priority, this one has a third priority. So 1 2 3, that has a anti-clockwise direction, so configuration is S. Now coming to this one, so first priority, second priority, third priority, this one has a clockwise direction, that means here R configuration. So here exactly opposite configuration, so these two are the mirror images, so these two are the enantiomers. Okay, so one of the most important and the previous national wide question, I think IIT-JEE or GATE examination, it is one of the previous question from given from the our famous book, that is Jonathan Clayden. Okay, here some more examples are there. Here BH3 again here that can reduce the amides. The BH3 is the most selective reagent for the amides as well as carboxylic acids. Okay, so that amide is reduced to amine. Now in this case there is a ester functional group and there is a amide functional group. So by using borane, that reduces only amides or carboxylic acid in the presence of the esters. So here also the product is the amide reduced product. So ester remains same in this reaction also. Okay, so thank you for watching. In next video let us discuss the partial reduction about the dibol H. Thank you for watching. Please subscribe my channel for more videos.